Okay, so let us start. So, in last class we had our last section, we had studied UV visible spectroscopy. We went into detail of UV visible spectroscopy. Just to refresh your memory, the first thing, where transition happens. So, you have a HOMO and LUMO, transition of electron happening from highest occupied molecular orbital to lowest occupied molecular orbital, that is absorption. Now, absorption depends upon many things that we have looked at. It is a distribution of electron, how it happens, then what is the effect of solvent, then we had looked at how the solvent changes this. If there are more than one chromophore, it can coming as addition, then we can deconvolute it, and many things, many application of this we had looked at, how you can use in drug discovery, how you can use in forensic science, how you can use in food, right, quality, food quality testing. Taking an example of turmeric, we have also showed how you can use in various aspects. So, today after the depth like a discussion of UV visible, we will transition into another spectroscopy which is very, very important and phenomenal, called fluorescence spectroscopy. Now, fluorescence spectroscopy, as you know, that we have sent the electron to higher excited state, right. Now, electron, nobody wants to be in excited state, right, nor even you. You do not want to be all the time excited state, right, you want to come to ground state. Electrons similarly wants to come to ground state, but ground state आने के भी कुछ condition होते हैं. It cannot just come like this, just it will not fall like this. The phenomena with which it comes from the excited state to ground state is known as fluorescence. So, let us look at what actually it constitutes, right. So, absorption we have looked at, it is an instantaneous event. What was the time scale of absorption spectroscopy? Any of you remember? Femtosecond, excellent, 10 to the power minus 15 second. It is a instantaneous event, it occurs so fast that there is no time for molecular motion. What was this principle we discussed? No time for molecular motion during the absorption, Franck-Candon principle, right. So, thus absorption spectra are not sensitive to molecular dynamics. Nucleus doing whatever motion, it does not depend in the absorption whether the nuclear is making any motion, right. So, it is a absorption is independent of nuclear motion, and it only provides the it depends upon solvent and like a shift that spectrum we have seen because of solvent effect, and the molecule that absorbs is called chromophore, right, chromophore. So, in contrast to say absorption, if emission has to happen, right, excite, गुस्सा सबको जल्दी आता है, you get excited, but to calm down it takes time. Similarly, when electron has to come down to the ground state, it takes time. It is not instantaneous as compared to the absorption. So, it takes time, it is a longer time, and the time, length of time that a molecule come back from the excited state to the ground state, that will be slower than the absorption. How much slower? It is a nanosecond time scale, happens, and there is another dynamic process in solution that happens. It depends upon the solvent effect, the what is the surrounding and all those that we are going to discuss. So, I will come back if you possible to the diagram called Jablonski diagram. If you remember this, we have discussed this, right. These are electronic states. Electrons are going from the ground state to first excited state, second excited state. This time scale is in femtosecond. Now, once it has gone there, it has reached somewhere here, and we also discussed why it is broad, right. This line is not going just from here to here, they can be going to somewhere here, 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 and that gives you broad spectrum in the UV visible. Now, when it has to come back, all of them come back to this state, which is S1 state, and then it comes back to ground state, right. So, when you get excited, means when you are angry, instantaneously you get angry, that is the excited state suppose. When you have to cool down, it takes time. Mind thinks this is not right, this is not right, you take time and then you slowly cool down. That is what fluorescence does. So, typically this time is nanosecond time scale. How it happens, that is explained in Jablonski diagram. We are going to discuss this in the fluorescence, and that when it comes down from this state to here, that is essentially the fluorescence. It is a radiative process. Radiative means that emits light, that is a radiative process, and there are many competitive non-radiative process that happens in the fluorescence, right. Many non-radiative, jahan light nahi emit hota, that is a non-radiative process, happens when it comes back, right. Those are not productive one, right, chup chap, just it emits the light, that is a non-radiative process. So, let us look at what is happening. So, remember when it is emitting light, it is reporting something, reporting about fluorophore, reporting about environment, reporting about how fast, how slow it is happening, reporting about many things like local environment, fluorescent effect and all those. Therefore, over the year what has happened, and this light you can capture over the year, because of this interesting property of emission of light by just giving some light, fluorescent light, this fluorescence has been used in many of the application. In biological application, fluorescence, right, all the, if you want to see a molecule inside the cell, you have to just put a fluorophore, you can look at that. So, in developmental biology, in neuroscience, in biophysics, biochemistry, whatever biological science you have, you see a fluorescence. Whatever chemistry you have, it is a reporter molecule. So, in chemistry, in biology, in forensic science, in many of the places you use this concept of fluorescence, right. So, let us start little bit backward. So, first let us start with something called luminescence. Luminescence, it is a light emission from any substance from electronically excited state. As I said, electron went from ground state to excited state, right. Now, it has to come back. When it comes back, right, light is emitted, and light, when light is emitted, this is called luminescence. Broader sense is luminescence. So, luminescence can be various type. One is fluorescence, it occurs almost immediately after excitation. Immediately means not that fast. So, 10 to the power minus 15, that is a femtosecond is absorption, this is nanosecond, right. So, nanosecond, that means when it goes to all the excited states, slowly, if you remember, it comes down to the first excited state, wahan se niche aata hai, that is a fluorescence. So, it happens in nanosecond time scale. The another kind of emission that you might have seen called phosphorescence, right. How many of you have experienced this phosphorescence? It is a delayed fluorescence. माने थोड़ा टाइम लगता है, इट्स नॉट दैट इंस्टेंटेनियसली, दैट टेक्स एंड लास्ट फॉर सेवरल सेकेंड्स, मिली सेकेंड टू सेकेंड. फॉस्फोरेसेंस मैं बताता हूँ उसको क्यों डिलेड या टाइम लगता है, दैट आई विल डिस्कस. देन देयर इज समथिंग कॉल्ड chemiluminescence, light produced from chemical reaction, right. Something is reacting, it produces light, there is no heat, chemical reaction, light produced, that is a chemiluminescence, right. So, you can use this in forensic science, like luminol reacting with blood, you can find it out. Forensic science, crime hua hai, blood gira hai, you can find it out using chemiluminescence. You add some chemical, some light is coming, you can find it out what is happening. So, this is chemiluminescence. Then there is another kind of luminescence called bioluminescence. It is a form of chemiluminescence found in living organism. Jugunu, right, what is this called? Fireflies, right. So, fireflies is an example of deep sea, some deep sea creature, jellyfish or something which gives you color. Fungi, some fungi gives you color, that is some living organism giving you color, used for like a communication, camouflaging, attracting prey. These are bioluminescence. Camouflaging, all of you know what is camouflage? Okay. Do you know why army wears certain kind of dress, right? उनको जंगल में छुपना होता है, so they matches their dress with the environment, right? So if you can hide with in the surrounding of the nature, that's a camouflaging. Any other example? Octopus? Okay. और गिरगिट की तरह रंग बदलना, camouflaging, changes its color. So those are again example of camouflage. Attracting prey, it's an interesting way of how organism right develop this mechanism so that light दिखा के भोजन कर लेते हैं, right? So that's an interesting example. Then electroluminescence, it's right there, right? So electric current or field, LED or OLED. What is OLED? LED तो light emitting diode. OLED, organic light emitting diode. आजकल टीवी स्मूथ फ्लैट टीवी आ गया है, that's are consisting of these. Then radioluminescence, it's a triggered by ionizing radiation used in like dial wattage, right? The triboluminescence, light emitted when material is scratched, crashed, rubbed, all these can be triboluminescence, seen in sugar or adhesive tape. When peeled, you can get the color. And finally, sonoluminescence, it's provided by sound wave. So depending upon from which phenomena light is coming, you can name them. Bio, coming from living organism, electro or chemoluminescence, coming from chemical reaction, electro from electric field, then radio from like a radiation, and like a scratching or crushed one, right, turbo, and some sonoluminescence coming from sound wave. So these are different kind of radiation that get emitted. In all of the case, absorption happens directly. When they are emitting light, depending upon what is the way of they are emitting light, that is called luminescence. After luminescence, giving you example of luminescence, I will stick myself to mostly fluorescence. Right. So fluorescent molecule that emits the light. Fluorescent molecule that emits the light can come in different shape and size. The protein, for an example, biomolecule can have intrinsic fluorescence. माने उसमें है, that's an intrinsic one. Some residue, like whatever we named, tyrosine, tryptophan, have an intrinsic fluorophore. You can have some protein which has fluorescence. So these are some of the fluorescence that, and they absorb at some place, emits at some place. So they are used. If you look at all of these, tryptophan is a fluorescent molecule, 2-aminopurine, pyrene, all of these are fluorescent dye, and they have a distinct wavelength where they absorb and where they emit, right. So that's our fluorophore molecule. Intrinsically fluorophore, we know that protein has some residue which is intrinsic fluorophore. Intrinsic fluorophore means like they have this. Extrinsic fluorophore means that you attach to them. So these two kind of fluorophore we have, intrinsic fluorophore, extrinsic fluorophore. So proteins or the biomolecule can have an intrinsic fluorophore. Chlorophyll, the green pigment that you see in leaves, right, it's a intrinsic fluorophore. So that again a fluorescent molecule. The other molecules can be synthesized, the dye, right, fluorescent shirt somebody wearing, that's not intrinsic fluorophore, but you can synthesize those dyes and you can stain your cloth with that fluorescent color, and you can go to party wearing fluorescent green, yellow color t-shirt, right. So that's extrinsic because we chemically synthesize those dyes, those will be fluorescent. So dye or tag can be attached to non-fluorescent system, and there is an entire catalog of the molecules that can fluoresce at different wavelength. Organic solvent molecules have a aromatic ring. So you remember, for absorption also you require unsaturated electron from where they can jump. So these fluorescent molecule which is giving emission are essentially because they have absorbed somewhere. So these are having similar kind of phenomena, aromatic rings, pi conjugated electrons are there, and then depending upon shape and size on the structure of organic dye can emit the UV light into visible or even near IR. Okay. So, that is a absorption and emission. So, mostly there are some molecule which will be called fluorophore that first absorbs, that is called absorption or absorption spectra, right, excitation, we call it excitation. UV visible we call it absorption. In fluorescence, that is a connotation is slightly different, it is called excitation spectra, we excite the molecule, and once they come back they emit something that is called emission spectra. So, if you look at the right hand, these are different fluorophore and their emission spectra, they are changing all over the wavelength from say blue all the way to near IR, that is a emission spectrum of the fluorophores. So, these are fluorophores. Now, what is the historical perspective of fluorescence? You know, all the research happened because of curious mind. Somebody was discovering and putting it. I will not say these are the first one, but they in the modern science they have documented for the first time that this is the way. So, British scientist Sir John Frederick William Herschel reported phenomena first, later on Stokes in 1852 at the University of Cambridge. He reported something is happening and they documented it well, right. So, what they took it, the source of UV light which is coming from sunlight, right, and a blue glass filter, because what they want to do, sunlight has all the light and filters like it make it slightly kind of not monochromatic, but slightly I would say restricted in the wavelength that they used, and this filter transmitted light below like a UV filter, so below 400 nanometer. And they did the experiment where put the quinine. So, light was the UV light or blue light was shining on the quinine, and that was incidence lights, and then prevented receiving from the detector, that is eye, by an yellow glass of wine. So, you can think of the experiment that is done, right, all the basic things, sunlight already there, blue filter they got it, quinine dye, and then they are absorbing using a bottle of or glass of wine filter. Quinine fluorescence occurred 450 and that was easily visible. So, that is the experiment that he did. Sare Jugaad technology se he did a fantastic experiment to show that fluorescence is happening. So, light was shining which was blue, but what it was emitting is 450 and it was filtered, and his detection device is just eye filtering and looked at that. So, this is the quinone. So, now in terms of the modern science, if you look at, it was absorbing somewhere around 250 or 280 and another absorption it was around 350 and it was giving emission which was around 450. So, that is the, so this that's the absorption happening. Now, you look at what two things in this experiment we did. There is a incidence light, uska wavelength kya tha? Blue. There is a emitted light, uska wavelength kya tha? Yellow, right, 450. Why there was a shift? Right? There is a shift, right? What it was used to excite, what it was used to emit, right. So, that difference is coming, and therefore, excitation spectra is at 300 and emission is 450. So, emission is shifted by say 150 nanometer, right. This shift, because the other guy explained this on his name, this is called Stokes shift, Stokes shift, right. So, that is what. Let us go back to again the board and let me explain you why it is shifting. So, you see same molecule we are using here to excite, one light, two light for an example. I am saying that when it is coming, it only comes from this section, ये बाकी loss हो गया है कहीं तो, right. So, you remember the wavelength delta mu equal to delta E. Now, for excitation this was our delta E, for emission this is our delta E, समझ रहे हो. So excite करने के लिए we require more energy. Is that correct? Because delta is for emission. So what will happen to wavelength? So some light, some energy is lost, and therefore what is coming. So now you can appreciate when we excite, your wavelength is shorter than when it is emitted, and this shift is called Stokes shift. So this discovery laid the foundation of modern fluorescence spectroscopy. It is introduced the concept of energy loss. Energy is getting lost between absorption and emission, and this is the central for like a central concept in fluorescence. So whatever energy was used for exciting, that does not remain when it comes as a fluorescence. बीच में लॉस हो गया, एनर्जी का लॉस हो गया. So your input is x, output is y. So what is efficiency? Y by x. जितना y by x percent or y minus x, sorry, x minus y, whatever. So you put the 100 like a unit for exciting, you are getting only 40 unit for emitting, right. So 40% efficiency you get when emission is happening. First, lambda is shifting. Second, energy is getting lost. So two things are happening. One is shift in the spectra, which is called emission spectra. Second, the efficiency drops down. That is gives an important phenomena which is called quantum yield. So we will be looking at this. You remember these two things, Stokes shift and quantum yield, right. So emission, let us go back to what is happening in emission.
Why is it not showing up in the spectra?
That is what I am coming to. I will detail where it gets lost, right. So I give you an analogy. Excitation, you go to excited state instantaneously, but you lose it, right. There is something that similarly fluorescence happens. So it is lost, something called internal conversion. I am coming to that in a moment. So emission is a powerful spectrum that is used for any analytical technique to study the light that is getting emitted from the molecule excited state, first excited state of that. The transition from higher energy to the lower energy state. Here to here light is getting emitted, that is what emission spectrum. So in absorption what we are doing? We are exciting, some photon is absorbed. In emission slightly less frequency is emitted. So less photon is. So that's what is happening. Characteristic of the element and compound involved. How much it emits, that depends upon compound, right. It could be possible, because all molecule cannot be fluorescent. It could be possible that one molecule absorbed X amount of light, did not emitted anything, that will not emit anything, it just absorbs but does not emit anything. Some molecule can absorb only emit 20%, some absorbs emit 80%. So this property of or ratio of emission and excitation is a molecular property. Therefore, all molecules are not fluorescent in the nature. There are only selective molecules are fluorescent, and therefore fluorophores are only can be counted on the fingers. All molecules are not fluorescent, right. So the emission can provide insight. So if it is like as I was saying, it is coming from the first excited state to the ground state. So emission that is happening from this first excited state to the ground state tells a lot about the molecule. First, its electronic states. Second, its environment. What is the environment? Third, in which solvent is there, right. So all the property are given by this one fluorophore, which is somewhere sitting in the experiment. It can be protein, it can be cell or something. So you can use this spectroscopy not only for understanding the molecule, but it is a surrounding itself. It is a reporting to the whole environment, and therefore this becomes a powerful technique. Okay. Now where the energy gets lost, right. I will again have to go to Jablonski diagram where the energy can be lost. So as I mentioned that all the radiation will not come to the ground state. Whatever comes, we will call them radiative emission. Whatever just get lost, we will call non-radiative process. So, radiative means light is emitting, non-radiative चुपचाप शांत हो गया, right. So, that is non-radiative process. So, where it gets lost, let us go back to the again Jablonski diagram. So, for excitation we use this going from ground state to all sorts of excited state. First electronic excited state, various vibrational state, various rotational state. When it is coming back, I said only from here it emits, but यहाँ से यहाँ कैसे आता है? It just come by non-radiative process. This is called internal conversion, IC. Internal conversion, IC. Just relax without giving any light. This comes to the first excited state, chupchap, without giving any light. That is called internal conversion, IC, internal conversion, right. Then when it comes here, when it comes from S to S0, it does not only come to S0, it can come here, 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 all sorts of things, right. So, when it comes here and giving light, that will be called fluorescence, because this is radiative process. It is also possible that from here it just comes without giving any light, right. Nobody has forced it to give it light, it can come without giving any light, that is called quenching, right. Now, there is another phenomena that can happen. So, this is again non-radiative, this was radiative, this is non-radiative. एक और phenomena होता है, electron, right, there are two electrons here, ऐसे, ऐसे. There are two electrons here, up and down. What is the spin multiplicity here? Singlet state, 2s plus 1. ये क्या है? 2s is 0 plus 1 singlet, that is a 1. This is S1. So, अगर electron, this electron moved here, it is still up, right. The remaining was down. So, this is again 2 electrons, 1 up, 1 down, this will be called singlet state. If it goes to here same like this, it will be called singlet state. But suppose while coming back, palti maar diya, nobody has stopped it. So, it becomes like this. Now, the down one is like this and top one is also like this. What is the spin multiplicity now? 1, 2s plus 1, both are. So, this is called triplet state, right. Electron has flipped. So, this is called 2s plus 1, that is 2 multiplied with 1 plus 1, triplet state. So, here it can also possible that it goes from singlet state to triplet state. This phenomena is called inter-system crossing, ISC, right, ISC, inter-system crossing. It just flipped from singlet state to the triplet state. It is called inter-system crossing. It takes time to go there. Now, suppose this guy comes from triplet state to the again ground state. So, it takes time, right, it takes time flipping. Now, if it comes from triplet state to singlet state, again it has to, and therefore, it has to flip, and it is a process that takes time. Therefore, phosphorescence, triplet state से अगर ground state है, that is called phosphorescence. It is a radiative process. If it is radiative process, it takes time, it is delayed. Fluorescence is in nanosecond, phosphorescence is in millisecond to second time scale, it is a delayed. It is also possible that from triplet state it goes back to again singlet state, right. It was like this, in triplet state it becomes down, again it can go back and then it comes and gives radiation, that is called delayed fluorescence, क्योंकि flip flop करने में time लग गया. So, it is called delayed fluorescence. So, if you look at there are too many competitive process that is happening simultaneously. After electron absorbs in absorption spectroscopy, non-radiative process is like internal conversion, quenching, right, quenching just, or even it can without giving any light it can come back, that is again just relaxation without radiation. So, all of them are non-radiative process. The radiative processes were two, fluorescence and phosphorescence. So, if we summarize this, what are the competitive one and what are non-competitive, if you what is the competitive to fluorescence? It is a internal conversion, it is a quenching, it is a inter-system crossing, it is a non-radiative, all these competes. So, what it says that the fluorescence efficiency can also vary from the molecule to molecule, because there are many competitive process to bring it down electron to the ground state. So, molecule can partially dissipates its energy, right, by undergoing conformational change, right, flip flop and all those that we vibrational relaxation, just coming internal crossing or something like that. But when it comes from S0 to S1, that is radiative and that is called fluorescence.